Alright, we're going to cover random variables and specifically get into discrete random variables and how we can use them to answer some questions here. So first up, when we say random variable, it's specifically quantitative. And like I said, we're going to focus more on discrete quantitative variables. We'll get into continuous a little bit later in the chapter. But what that means is, remember, a variable is just a characteristic of interest in an experiment. Specifically, we talked about earlier this unit random experiments when we were introducing some vocab to probability. And so a random variable assigns a number to each outcome in the sample space of whatever random experiment we're working with. And what we're going to talk about first is just some weird notation. So when we talk about defining a random variable that's describing our outcomes, we're going to use a capital letter X, and then the outcomes that are possible are going to be our lowercase with our subscripts, just like specific term values, the first, the second, the third, and so on. So when we write out a probability distribution, which gives you the outcomes that are associated with each of their individual probabilities, then we're going to see like a P of X equals X, and I'll show you how that looks here in an example in a minute. Specifically, a discrete probability distribution is that same probability distribution where we're counting the variable is countable. Remember the difference between discrete and continuous. Quantitative variable, discrete is something we say that we can count, like the number of siblings or money, whereas continuous is something we measure, like height or weight. So, last thing here, and this one's quick, discrete uniform distribution. We've talked a little bit about shape of distributions. So we've seen symmetric, which means you can split it down the middle and it looks the same on both sides approximately. When we talk about a uniform, it's even more specific than that. So not only if you split it down the center, it's even all the way across, meaning in a probability distribution that each of our outcomes have the same probability or likelihood. So for example, we can talk about rolling a single die being our random experiment, and the random variable being the number that the die shows. So the outcomes that are possible are 1, 2, 3, 4, 5, 6, and the lowercase letters S1, S2, S3 would represent those. Then the probability, capital P, of that random variable distribution is 1/6 for all of those separate outcomes. So that would be considered uniform since each outcome is equally likely. Okay, so that's all it means to be uniform, is probabilities throughout are all the same. So let's look at an example here. Two dice are rolled, and we're going to let X, our random variable, represent the sum of the two values that face up on the dice. So this one is not uniform because we're talking about the different sums that are possible. So if you remember a situation where you're rolling two dice, we have 36 different outcomes. That comes from, there are 6 outcomes for the first die, and repeated twice, 6 outcomes for the next one, so there's 36 total. Okay, so when we're talking about probability, it's always a good idea to calculate the total first. Then, when we're talking about, excuse me, when we're talking about calculating probability with different outcomes, knowing the sample space may be helpful. Now, the sample space or the outcomes of the probability distribution based on our random variable is not the same sample space as the experiment of 2 dice being rolled. Okay, so let's get into that a little bit. Let's, over to the side here, just talk about the sample space for rolling 2 dice. So I could have a 1 with a 1, or a 1 with a 2, 1 with a 3, 1 with a 4, and so on, all the way till we get to 1 with a 6. Similarly, I can have a 2 with a 1, 2 with a 2, 2 with a 3, and I'm just listing out those 36 different outcomes. Now, it's not always necessary to list them all out, but if you're taking your test on paper, might as well, because then you can circle and work with them and not have to repeat. So I'm not going to fill out this entire thing here. I'm just going to show you enough for the pattern. So we go all the way to the row with 6, and it goes to 6, 6. So there's a 6 by 6 gives me my 36. What I want to talk about is the sum. So my lowest sum would be adding these two digits of 2, and my highest sum would be adding these two digits, 6 and 6, to 12. So what we're going to do is talk about our notation again. Our outcomes are, excuse me, the lowercase letters. So we can put x, or a lot of times you'll see x with the subscript I, so I'll just write xi. And our notation for these probability distributions will be p, capital X defining our random variable, equals xi to just show we're talking about the entire distribution of all the different x values of the outcomes. So the lowest sum is 2, and we're going to hit every sum up until 12. So we know we have one way to hit a sum of 2 and one way to hit a sum of 12. So I'm going to start with those. Probability then would be 1 out of 36. And over here again, 1 out of 36. Okay. Then we're going to look at the next one. We want to talk about a sum of 3. Well, we could get that from a 2 and a 1, or a 1 and a 2. So there are two different outcomes here. A sum of a 4, I could do a 3 and a 1, a 2 and a 2, or a 1 and a 3. So there are 3 outcomes there. Okay. And then hopefully you're seeing a little bit of a pattern here. So the next one, when we're talking about a sum of 5, would be this 4 and a 1, this 3 and a 2, 2 and a 3, 1 and a 4. So there'd be 4 here. The next one would be 5 total ways. The next one is 6 total ways. From this diagonal all the way to this one. 6 and 1, 5 and a 2, 4 and a 3, 3 and a 4, 2 and a 5, 1 and a 6. And then when we get to a sum of 8, it starts decreasing again. So there's 1, 2, 3, 5 different outcomes for that one. And then 9, there are 4 ways. Then 3 ways. 2 ways for 11, 5, 6, or 6, 5. And then that last way that we already talked about. Now, when we talk about outcomes in a sample space in general, the sum of your probabilities must be 1. So just to verify that we got all of those individual probabilities correct, we're going to go ahead and add that up. And there we go. It works out. Now, just so we cover all possible questions, this was the probability distribution. So this is what it was asking for, is make a nice table with your headings, your different outcomes, and the probabilities that are associated with it. I'm going to add some borders here, and then I'll highlight it to say that's my answer for the question it actually asked. But you may also be asked something that kind of works your definition backwards. So suppose I give you this probability distribution, and I give you just all of the cells except for this one. If you were asked to find the probability associated with that sum of 5, not necessarily a sum of 5, but the 5 that goes with this particular example, what we would know is that these extras have to add up to 1, and so right now we're adding up to this 0.889. That would be just 1 minus that sum to get the leftover. Okay, so you may be asked something like that for a problem on your homework, or moving on, as far as the test. Okay, so now we're going to create a probability distribution for the number of heads observed in 3 tosses of a coin. So this time they didn't define the random variable for us, so we're going to do that first. Okay, so we're going to let capital X represent the number of heads observed in 3 tosses of a coin. So if we talk about our sample space, when we're dealing with 3 tosses of a coin, I could get heads, heads, heads. I could have heads, heads, tails, or heads, tails, heads, or tails, heads, heads. So I started out with 3 heads, and then I showed what 2 heads could look like. Now I'm going to go to 1 head. So HTT, THT, putting that head in the middle, or it could be at the end. And then similarly, I could get all heads, but I could also get no heads, which is all tails. So those are my outcomes, and there are 8 total. Just like what we did up here, my total can be calculated by first flip has 2, second flip has 2, third flip has 2, and means multiply, so that's 2 to the third for 8 total outcomes. So we want to talk about the number of heads that are possible. That is 3, 2, 1, or 0. So when I set up my probability distribution with my xi and then p of capital X equals xi, my outcomes that are possible are 0, 1, 2, or 3. And then now that I have this nice sample space, I can calculate the probability. So 0 heads, there was 1 outcome that looked like that. So 1 out of 8. 1 head, there were 1, 2, 3 that looked like that. 2 heads, there were also 1, 2, 3. And 3 heads right here is 1 out of 8. Again, we want to verify that we did this correctly, so I'm going to give this sum here and make sure it actually adds up to 1. And it does. Okay, so my probability distribution, add my framing, and highlight. Okay, so now what we're going to do is just check with the examples and decide if these are valid probability distributions. So the first thing we're going to check is that the individual probabilities that go with the outcomes are actually valid probabilities themselves. The second thing we'll check is that they sum up to 1. And we have, this one's going to be pretty obvious, but we have mutually exclusive outcomes here. So nothing repeated essentially or overlapping. So here, first, if we go through these probabilities, this is a problem right here, this 4/3. So that makes this one a no. Probability cannot be larger than 1. This next one, all of our individual probabilities are good. We have different separate outcomes. So the only thing we have to check is that these actually add to 1, and they do. So this one is a yes. So all valid probabilities, and sum of the probabilities is 1. Okay, on this last one, we've got an issue right here. Okay, probability cannot be negative. So even though these add up to 1 when you add them, we have to check that the individual probabilities are valid first, so this is a no. Probability cannot be negative. Okay, so that's it for that one. On number 3, we've got KJ Johnson, a computer salesman. During the last year, he kept records of his computer sales for the last 200 days. We're supposed to create a probability distribution from the given frequency distribution and answer the following questions. So all of the probability we've done so far is a theoretical probability. It's the traditional calculation, the number we want over the total. But another way we can calculate a probability is using empirical data, which is just a fancy way to say we'll use the relative frequencies to define our probability. So here they give us a frequency table saying there were 40 days that had 0 sales, 20 days that had 1 sale, 60 days with 22 sales, and so on. So in general, just like with our probabilities up above, the first thing we want to do is figure out our total. And that's going to be the sum of our frequencies. Now in general, on this one, we know that our total is 200 because they gave that to us, but I likely will not, so it's good to know how to calculate that. That's going to help us with our probability, which was our relative frequency. So we're going to add to our table here. And we're going to take our relative frequency, or calculate our relative frequency, by taking our frequency over that total. Just make sure that you lock in that total by putting the dollar signs around that C for the 200. Okay, from there we can drag down. And of course these have to add up to 1 as well, so I'm just going to drag that over to check. We're good there. So from here, we want to know what is the probability that this salesperson will sell at least 2 computers each day. At least 2 means we want 2 or more, so 2 or 3 or 4. So we're going to take the sum of those 3 probabilities that we just found. And so our probability is 0.7. Now you can change that to a percent if you want, but probability is valid as a decimal. The next one, the probability he would sell at most 2 computers, so that means could be 0, 1, or 2. So the bottom half here. Okay, and that's 0.6. Because the 2 is included in both of these, we do have an overlap. These would not be considered mutually exclusive. They would not be considered complements. If I wanted to restrict this so that they were complements, then I could change one of these to get rid of the 2. So I could say sell at most 1 computer each day, and then my probability here would change to 0.3 with 0.7. They add up to 1. Okay. So now we're going to do a little bit more with these probability distributions. Again, specifically discrete ones. We'll move on to the continuous ones in a couple days. So I'm going to go back to our example with the sum of the 2 fair dice. So we decided that the lowest sum possible was 2 and the highest was 12. So here was our probability distribution table. Now, what we're going to talk about is the expected value of the distribution, the variance, and the standard deviation, because those were our measures of center and spread that let us analyze that variable together. So as a reminder, we've done some work with grouped data before, and I like to relate it back to the graph. When we talk about a discrete variable, it's going to be represented as a bar graph rather than a histogram, since each of those values can be separated. So we've got 2, 3, 4 as separate sums, and when that happens, when we have a bar graph or discrete data, if this is in the regular frequency rather than what you see here is the relative frequency, then we can go and take and make a raw table out of it. So that's what I've done here, is I've spread this out. Remember, we said that there was only one way to get a sum of 2, so there's 1, 2. There were 2 ways to get a sum of 3, so there's a 3 and 3. And then the next one was 3, so there are 4. And so if you have the raw data, we know we can calculate the mean using Excel. So do this with me here. Add a little column for raw, and we're going to go through these Excel formulas. Equals average for mean, and we're going to calculate the mean here. Okay, matches up with the table. Okay, then we're going to do equals variance. Since this was the entire probability distribution, we're going to use this based on a population. And then calculate that from the table of raw data as well. And then 2 ways to get the standard deviation. One is take the square root, but we're going to practice using the Excel formulas, so standard dev.p for that. Now, what I've done here, it looks messy, but I want to show you how these formulas work. It's going to be similar to the work we did with the group data. So here, when we were doing the group data before for mean, we took x times the frequency, and then we had to divide by the number. Well, remember, this p of x, this probability, is also like a relative frequency. So the total is already built in here. Okay, so we don't have to divide in this formula because it's already built in. So it says take x, which is our numbers 2 through 12, multiply it by the probability. Okay, so that's what this one is here, if you notice. It's just the product, that times that. And you can just use the times sign. You don't have to use the equal product. Drag it on over. And then after that, to get the mean, you just add up that row or column. That's it. And you'll notice it's the same 7, gives us the same answer as we did with regular Excel when we had the raw data. Okay? With variance, variance is calculated by, remember it's related to our standard deviation. So we calculate the deviation of each of those numbers from the mean. So this value, we're subtracting our 7 from, and then we are squaring it. So here I had 2 minus 7 is -5, squared is 25. I did that all in one go for this table, but then again just dragged it across. Once we have those, we have to weight them by the frequency and divide by the totals. Again, this probability has that total built in. So we're going to multiply it just by our probability from the table. So that's what is here, is those two things, drag over. And lastly, we can add them all up. So for that, you can see the sum of that row. Standard deviation, once we have our variance, we're just taking the square root of. Okay. Now, what is different with these formulas versus the grouped interval data is these are not approximations, they are precise. They're exact values because we had our discrete values. These weren't estimates based on the midpoints, they were the actual value. All of those really were 2s. All of those really were 3s and 4s and so on. So these ended up being exactly like the raw values because we could create the raw values from the distribution where you can't when it's continuous. Okay, so those ones will be estimates again when we get to that. So let's practice with this one. So this was our values from problem number 3, the computer salesman. We're going to find the expected value, which would be the expected number of sales. Now, the expected value relates to average, so when we get through with our process, we should see a number that falls between 0 sales and 4 sales because that's our lowest and highest values if we think about our original set. Now, this is why the formula matters. We don't want to spend the time to write 40 different zeros, 20 different number 1s, 60 different number 2s, and so on to be able to use the Excel formulas. Okay, so it says take the x value times the probability, which we already calculated up above. So we're going to grab the x value, times it by the probability, and that gives you the weighted total of 0. So it says there's 0 40 times, but y'all, that's still 0. Then we're going to do the same thing with the next one, and you can just drag that down since we did some cell select there. Okay. And that gives us our weighted total divided by our total, since the probability has that built in. So our last stage is just to add that up. And remember, if we did this right, should fall between 0 and 4. So the typical expected value is 2.1 sales per day. Now again, that doesn't mean a computer salesman is actually going to hit 2.1 sales. These are discrete. The only possible number of sales that are possible are 0, 1, 2, 3, or 4. So they're either going to get 0, 1, 2, 3, or 4. They can't get 2.1. That's just a typical value. It's an average. Next thing we're going to do is see kind of instead of a measure of center is take a measure of center and also use measure of spread to talk about interpreting different tables. So here we are confronted with 2 investment alternatives that give you uncertain outcomes described by the probability distributions in the table below. We want to know in the long run which plan will have the higher payout. So first of all, our higher payout is going to go with our expected value. If we just look at our tables here, we've got some of these, so I'm going to call this Plan A, but it's kind of like a portfolio when you're investing. A lot of times a financial manager will put the money that you're depositing into a portfolio, and so some of the shares you buy are in one stock, and then some of them are in the other, where one of the stocks is maybe more volatile but could be giving you more reward for your risk, and then some of them are more stable, and that portfolio together creates a balance based on what their customer is aiming to get in the time they deposit their money. So here, they have weighed their money in this way, where we've got these more positive or stable ones in the higher probability, and then we've got a riskier one here with the 0.2 and then 0. Again, these are things that happen maybe in the last year, 2 years, 3 years. Obviously, if we're investing money and you know it's losing money, you wouldn't put your money into that payout, or into that plan. But this is based on, you know, fluctuations that happen over time. So we're going to find that expected value just using the formula here. We've got our X talking about the payout. So what I didn't do up here that may help you is whatever you define your random variable as, your X, it may be helpful to just change that in the title. So here our payout is our X, and then we've got our probability for each of those different X values. So what we're going to do now is find the X times the P of X, and multiply those two things together. Then we can go ahead and drag that down. Okay, so from here, our expected value just wants us to sum those or add it up. Remember, when we're talking about the expected value, it should fall somewhere within the range of your X's. So our lowest number is negative 2,000. Our highest is 4,000. If we get a number that's not between those two values, something went wrong. So here we've got a $900 expected payout. Okay. We're going to do the same thing for Plan B so we can figure out the higher payout. So for this one, again, I'll change that to an X, and we'll do our X times P of X. Grab those values, and then drag them down. So this time, my sum should fall between negative 3,000 and positive 4,000, a little bit lower range here, but it ended up being a higher expected payout. Okay. But if we're doing this investing here, those negatives might be scary for some folks, because here 30% of the time you're losing 2,000. Here 30% of the time you're losing 4,000. Okay, so it has a higher payout, but also they look riskier based on those negatives that are showing up. So another thing that we can consider is the spread, or how the different payouts vary. Okay, so the 1,400 is what we expect, but sometimes it's going to be higher, sometimes it's going to be lower. There's variation. So to do that, we're going to calculate the variance and the standard deviation, our measures of spread. So for this, we're just going to extend out this table, and we're going to take our values minus the mean. So let's create a column here for X minus the mean. And that's my X over here. And my mean is what we just calculated with the expected payout. Again, we want to lock that in before we drag it down. Now, just for your notes, make sure you realize that this value here is your mean. Okay, I'm going to go ahead and highlight that so we can see it. It's got mu is the mean equals the expected value of X. So same thing over here. This is my mean that we'll use when we get to that side. Okay, then we're going to square those items, because we don't want, when we take and add up my deviations from the mean, those to cancel out. those pound signs there just means my column's not wide enough to take care of that big number. So we can just extend that out. And then finally, we're going to take our squares and multiply them by the probability. Now, we do want to be very careful. We're taking our squares and we're multiplying it by p of xi, the original, not the x times p of x. So just that 0.2. And then we're going to drag that down as well. Similarly, those pound signs are just because my numbers are so big. Final thing we're going to do to get my variance is just that sigma at the end, which is add them all up. Okay, so down here, my variance is $3,090,000 squared. Hopefully you remember that variance is my label squared because my more useful measurement of standard deviation is the square root of that. So square root, and I'll just grab this number up here. And then this one I don't need to wear labels, so you can just go up and hit that dollar sign if you want. Extend it out a little bit so it shows up. Okay, so that says that I'm expected to make $900, but that $900 may vary by about $1,800 on top of that. So it could be 18 higher or 1,800 lower. Okay, we're going to repeat that process over here just for practice. Let's us compare these two things. We're going to take our x minus our mean first. Remember, our x is our sales from over here, and our mean was this expected value down here that we're going to lock in. Then we can drag it down. Next thing our formula says to do is square those things. Raise it to that second power. Drag those down. Okay. After that, we're multiplying by the probability. Okay. Remember, we're taking our squareds that we just got times way over in the original table, the regular probability, then dragging that down. Finally, we're adding them all up. So my variance here for this one is $6,640,000 squared. And my standard deviation is the square root of that. Just in regular dollars. So this one, the expected value is 1,400, but it varies by 2,500 from there. Okay, so higher variation and a higher expected payout, which is what these questions are asking you about. It says, which plan has the greater chance of making a substantial gain? That one was my plan B, since its expected value is larger. But plan B also has more variability, and that makes it more risky since its standard deviation is higher. Okay, so more standard deviation is more variability, which sometimes can indicate risk. Okay, last type of problem is dealing with like expected payouts. You'll have a couple problems on your homework that refer to kind of like game situations. So here it says, consider entering a raffle with one $500 cash prize, one $1,000 cash prize, and each player may only purchase one ticket for $50. There are 200 raffle tickets that are sold. We want to represent the financial net gains or losses with the discrete random variable R and construct its probability distribution. So the first thing, okay, is they tell us that R is representing our financial net gain or loss. Okay? So then we got to talk about what are the possibilities of things I could win, what are the things I could do for losing, and when I say net gain, means I have to subtract any of the payments that I made to win the money. So I'm going to write this out kind of in a strange way. So we know to do a probability distribution, we need our x and our p of x. So in this case, they have r. So I'm going to use r, and p of capital R equals ri for that. But what I'm going to do separately is I'm going to talk about our options over to the side here. So option 1, and I'll actually move it over a little bit so we have room. So option 1, we were talking about we could get the $500 prize. Option 2, we could end up with the $1,000 prize. Or option 3, we could have no prize. So when we talk about our different R values that are possible, with the $500 prize, if I want to consider the financial net gain or loss, if I'm winning a prize, it's going to be a net gain, but it's net after spending $50 on the ticket. So that would be $450 of my profit, essentially. Okay. Similarly, with the $1,000, I'm going to be winning money, so it's positive, but it's going to be $950 rather than $1,000 because I had to spend that $50. Now, if I win no prize, then I have no money, but I also spent money to get into the raffle, so that would give me a negative $50 for that one. And now, all we have to do is calculate the probability of each. That's where the 200 comes into play. So they give us the total is 200, and they are all equally likely, okay? So each draw is 1 out of 200. So there was exactly one $500 prize, so that's going to be a probability of equals 1 over 200. Similarly, there was one $1,000 prize, so equals 1 over 200 again. And then no prize, the leftovers, is going to be equal to 198 over 200. Okay, remember when you add these up, they have to hit 1. Okay, so that's 100%, it works out. They want us to compute and interpret ER, expected value of our random variable, our financial net gains. Okay, so our expected value from our formula up above is we take our R times P of R. So here times this, and then all the way through. And then we're going to do the sum to finish up. Okay. The expected value of the raffle is losing, or a loss of, $42.50. Okay. Now, I'm going to tell you anything dealing with a raffle or a lottery or like casino games, they will likely have an expected value that's negative. Okay. The purpose of a raffle is usually for a fundraiser. They entice people to buy it by offering these big prizes, but they also know that most people will not win those prizes. So while the consumer, the person buying the raffle, is likely to lose, that in return means the people running the raffle are going to earn more money than they're giving out. Okay, if you think about it this way, 200 times 50 gives you more money than you're handing out here. Okay, that's the goal, is making sure that you're actually earning more money than, you know, you're giving away, essentially. So the next thing we're going to do is just review. Well, actually, I'm going to go ahead and skip this problem because it's just review. I just want to make sure we can set up one more like this. Make sure you're really clear on how this works. Okay, so what I'd like you to do now is actually pause the video, read through number 6, and see if you can write out how you would express this probability distribution using this example that we did up here kind of for guidance. Okay, pause the video and try that for me, and then come back and we'll chat. So this time we're talking about the expected value, and it's talking about, again, winnings. So I'm just going to use x since they didn't give me a variable here. Is going to talk about the winnings that you have, or net gain loss. So here we've got our x and p of x. And we have only two options here. You can win $36 or you can lose $27. Those are my options. Now, if I go over here, my total for this one, hopefully you remembered from earlier when we throw 3 tosses of a coin, there are 8 ways to do that. And if we want exactly 2 heads in that is 36, and if not, you lose. So here we've got, this one will go with exactly 2. This one is everything else. Okay, so my probability of exactly 2 heads would look like 3 of them. Just to remind you, I could have heads, heads, tails. I could have heads, tails, heads. Or I could have tails, heads, heads. That's where the 3 is coming from. So equals 3 over 8. And I wrote else because these are going to be, remember, complements by definition if there are only 2, because the probability distribution has to add up to 1. So I can do equals 1 minus to get that other one. Okay, from there, okay, we can find the expected value. First times second. Drag it down and sum. Our answer for this one, just like the other expected values, has to be between our possible numbers of negative 27, 36, and it is. So this one, you're losing money as well, about 338. If it says you played this game 623 times, how much would you expect to win or lose? That's literally taking my number and multiplying it by my 623. So you would lose quite a bit of money. I'm going to hit the dollar signs. So it automatically rounds for me. Okay, and then Excel uses parentheses to represent losses, but that's a loss of $2,102. Okay. If you have any questions while you're working on your homework, as always, come see me.